Hello, my name is Eric Austin, and I'll be presenting my term project for mechanical behaviors of materials titled The Mechanical Properties of Chondritic Insoluble Organic Matter, a property space analysis for icy moon interior modeling. While this is an engineering course, my background is in planetary science. So for this project, I wanted to take a core engineering concept, the Ashby chart and material selection, and apply it to a major unsolved problem in planetary geophysics, understanding the interior structure of icy moons like Enceladus. To understand why this matters, we have to look at the problem modelers face. Saturn's moon Enceladus has a differentiated interior, an ice shell, a subsurface ocean, and a rocky, organic rich core. To model how this core behaves, especially regarding tidal heating and its moment of inertia, geophysicists need two critical mechanical properties: Young's modulus and density. Here's the critical gap. Insoluble organic matter, or IOM, makes up a huge portion of that core, but no one has ever directly measured its mechanical properties. Because of this, modelers are forced to use terrestrial coal and kerogen as proxy values, but chondritic IOM is highly cross-linked and extraterrestrial, meaning these Earth-based proxies might be leading our models completely astray. To solve this, I approached the problem through the lens of material selection. I constructed an Ashby chart plotting Young's modulus against density for various organic material classes. Within this property space, I defined an Enceladus Model Constraint Region, the target box where modelers expect the core material to sit. I then subdivided this region into three hypothesis-driven zones based on thermal evolution models. Zone A for primitive cold accretion, Zone B for moderate alteration, and Zone C for thermally evolved material. To actually test this, I performed direct measurements on IOM extracted from two meteorites. I used a KLA I micro nanoindenter to measure Young's modulus and an Anton Par UltraPic 3000 helium pycnometer to measure density. This allowed the comparison of real extraterrestrial data points to clusters of known terrestrial materials on an Ashby chart for the very first time. The results were incredibly revealing. First, I measured IOM from the Tarda meteorite, which experienced moderate aqueous alteration on its parent body. It landed squarely in Zone B with a modulus of 5.03 gigapascal and a density of 1.68 grams per cubic centimeter. Next, I measured IOM from GRO 95577, a meteorite that experienced extensive aqueous alteration, and landed in Zone A with a lower modulus of 2.82 gigapascal and a lower density. This reveals a clear trend in increasing aqueous alteration, disrupts cross-links, and introduces hydrated phases, which decreases both stiffness and density. Furthermore, both IOM samples sit at a higher density than most terrestrial proxies, proving that coal is likely a poor analog. Ultimately, this is the first empirical evidence that IOM mechanical properties encode the alteration history of their parent bodies. Looking ahead, there's still much work to be done. Currently, we've only measured two meteorite samples, and the GRO data is still preliminary. The immediate next step is to measure IOM from a broader range of chondrite groups to fully populate all three zones on the Ashby chart and to quantify the alteration property relationship. Additionally, to directly calculate tidal dissipation for these geophysical models, we need to move beyond elastic modulus and perform creep measurements to understand the material's viscoelasticity. In conclusion, this project demonstrates that engineering frameworks like the Ashby chart aren't just for building airplanes or bridges. They can serve as powerful diagnostic tools for understanding the thermal history of the solar system. I want to say thank you to Dr. Kate, Dr. Yu, and the Planetary Materials Characterization Facility. I'd be happy to take any questions. Thanks.